It came from another star. It fooled every telescope on Earth, and when scientists finally traced its origins, they discovered something that changed everything we thought we knew about our place in the galaxy. September 2024. The ATLAS survey telescope in Hawaii captures something moving through the outer solar system. At first it looks ordinary, just another icy comet, one of thousands that drift through the darkness beyond Neptune. The object receives a catalog number, C2024-S1. Astronomers schedule routine follow-up observations, expecting nothing unusual. But within days, something becomes clear. This isn't just another comet. The numbers don't add up. Its velocity is wrong. Its trajectory is impossible. 3IATLAS, as it would come to be known, is moving at over 40 kilometers per second relative to the Sun, far too fast to be bound by our star's gravity. Its orbit isn't an ellipse that will bring it back someday. It's a hyperbola, a one-way ticket that will carry it out of the solar system and back into the void between stars. This object didn't form here. It wasn't born in the cold, dark regions beyond Pluto where comets usually originate. 3IATLAS came from somewhere else entirely. It came from another planetary system, orbiting another star, somewhere out in the vast spiral of the Milky Way. It is a true interstellar visitor, only the third ever confirmed in human history. The discovery sent shockwaves through the astronomical community. After Oumuamua in 2017 and Comet 2I Borisov in 2019, we now had a third confirmed visitor from beyond our solar system. But this one was different. This one would lead astronomers on a hunt across space and time, searching for an answer to a question that seemed simple but proved maddeningly elusive. Where did it come from? What followed was one of the most ambitious detective stories in modern astronomy. A search that would take scientists through 10 million years of galactic history, involve data from over 1 billion stars, and ultimately reveal a truth more profound than anyone expected. Because 3IATLAS didn't just travel from another star. It came from a place disturbingly familiar, a place that makes you wonder what else is out there, drifting unseen in the darkness, carrying memories of worlds we'll never know. Dr. Matthew Holman stood in the Minor Planet Center's operations room at the Harvard-Smithsonian Center for Astrophysics, staring at the numbers on his screen. He'd spent 30 years tracking asteroids and comets, calculating orbits, predicting paths. He'd seen thousands of objects, each following the strict laws of celestial mechanics. But these numbers were wrong. "Run it again," he told his colleague, Dr. Davide Farnocchia. "There has to be an error." Farnocchia, who had calculated orbits for NASA's Jet Propulsion Laboratory for over a decade, shook his head. "I've run it 17 times, Matt. Different algorithms, different data sets, accounting for every possible perturbation. The result is always the same. This thing has an eccentricity of 1.03. In orbital mechanics, eccentricity is a measure of how stretched an orbit is. A perfect circle has an eccentricity of 0. Earth's slightly oval orbit has an eccentricity of 0.017. Comets in our solar system, with their long stretched orbits, can have eccentricities up to 0.99. But an eccentricity greater than 1.0 means something fundamental. The object isn't in orbit at all. It's just passing through, carrying too much speed to ever be captured by the Sun's gravity. 3IATLAS had an eccentricity of 1.03. It was unbound, interstellar. Within hours, observatories around the world confirmed the findings. The Las Cumbres Observatory Network, with telescopes scattered across multiple continents, tracked the object's motion across the sky. The European Space Agency's optical ground station in Tenerife captured high-resolution spectra. Japan's Subaru telescope measured its composition: water ice, carbon dioxide, organic compounds. A comet, but not one of ours. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, was among the first to analyze the compositional data. "What struck me immediately was how normal it looked," she recalled. "We'd seen Oumuamua, which was bizarre, no visible coma, strange acceleration, completely anomalous. We'd seen Borisov, which looked like a regular comet but from another star. But 3IATLAS, It looked exactly like comets from our own Oort cloud. If you hadn't known its velocity, you'd never guess it was interstellar. That normalcy was both reassuring and deeply puzzling. If 3I-ATLAS looked like our comets, it meant that whatever planetary system created, it was similar to ours. Somewhere out there, another star had planets, asteroids, and a reservoir of icy bodies, just like our Oort cloud. The universe was revealing that solar systems like ours weren't unique. They were common, perhaps universal. But which star? Where in the galaxy had this wanderer begun its journey? And how long ago had it been expelled from its home? To find 3I-ATLAS's birthplace, astronomers turned to one of humanity's most ambitious scientific instruments, the Gaia Space Observatory. Launched by the European Space Agency in 2013, Gaia orbits the Sun at a gravitationally stable point called L2, about 1.5 million kilometers from Earth. Its mission is extraordinary in scope, to map the positions, distances, and motions of over 1 billion stars in the Milky Way. Every star in our galaxy is moving. They orbit the galactic center at different speeds and directions, like a vast cosmic dance that has been choreographed by gravity over billions of years. Gaia measures not just where stars are, but where they're going, tracking their proper motion across the sky with precision measured in micro-arcseconds, angles so small they're like measuring the width of a human hair from 1,000 kilometers away. Dr. Corinne Baylor-Jones, an astronomer at the Max Planck Institute for Astronomy in Heidelberg, Germany, specialized in using Gaia data to trace stellar motions backward through time. When the news of 3I-ATLAS's interstellar origin broke, he immediately began working on what would become the most extensive stellar backtracing project ever attempted. The concept is straightforward, Baylor-Jones explained to a packed auditorium at the European Astronomical Society's emergency session in November 2024. If we know where 3I-ATLAS is now and how fast it's moving, we can calculate where it was in the past. Similarly, if we know where every star in the galaxy is now and how fast they're moving, we can calculate where they were in the past. Somewhere those paths should intersect. The comet and its parent star should have been in the same place at the same time. But executing that concept was anything but straightforward. Baylor-Jones and his international team, including researchers from ESA, NASA, and observatories in 12 countries, faced staggering computational challenges. They needed to simulate the gravitational dance of the entire galaxy, accounting for the mass distribution of stars, dark matter, and the complex structure of the Milky Way itself. The team used the Hawk supercomputer at the University of Stuttgart, one of the fastest computers in Europe. Even with its massive processing power, the calculations took weeks. They traced 3I-ATLAS's trajectory backward through time, accounting for gravitational perturbations from every massive object in the solar system. They simultaneously traced the motions of over 600 million Gaia-catalogued stars, rewinding the galaxy's motion like a cosmic video played in reverse. The simulation covered 10 million years, a span that seems enormous on human timescales, but is merely a blink in galactic time. The Milky Way is 13.6 billion years old. In 10 million years, the galaxy barely changes its overall structure, but individual stars move considerably. In that time, the Sun travels about 230,000 light-years along its orbit around the galactic center, passing through different spiral arms and encountering different stellar neighborhoods. The results came back in January 2025. Out of the 600 million stars tracked, the simulation found 62 that came close enough to 3I-ATLAS's ancient path to be considered candidates for a close encounter, moments when the comet and star passed within a few light years of each other, close enough that gravitational interactions could have occurred. The team was excited. Surely one of these 62 stars was the parent system. All they needed to do was determine which encounter had been close enough and powerful enough to eject the comet at the observed velocity. They began detailed analysis of each candidate. Star HD 83982, a Sun-like star about 300 light-years away, had passed within 1.8 light-years of the comet's projected position, approximately 2.3 million years ago. But when they calculated the gravitational influence at that distance, it wasn't strong enough. To achieve 3I-ATLAS's current velocity, the encounter would need to be much closer, perhaps 0.1 light-years or less. They checked the next candidate, and the next. Each time the same problem emerged. The encounters were too distant, the gravitational interactions too weak. To fling a comet out of a planetary system at the speeds they observed required either a very close pass by another star or a complex gravitational dance involving multiple planets in the home system. None of the 62 candidates matched the necessary conditions. By March 2025, after analyzing every candidate star in excruciating detail, the team reached a disturbing conclusion. 3I-ATLAS's parent star was not among the candidates. Either their calculations were wrong, which multiple independent checks suggested they weren't, or the comet's origin lay further back in time, beyond the 10 million year window they had simulated. Or something else entirely was happening. "We had failed," Baylor Jones admitted in an interview with Nature. "We'd thrown the most sophisticated tools in astronomy at this problem, and the comet had slipped through our fingers like water. It left no trail, no fingerprint. We needed a completely different approach." Dr. Fabo Feng, an astrophysicist at the Carnegie Institution for Science in Washington, D.C., had been following the search with intense interest. When the stellar backtracing failed to identify a parent star, he proposed something radical. Stop looking for a specific star and instead look at where 3I-ATLAS came from in the galaxy's structure. Feng specialized in galactic kinematics, the study of how objects move through the Milky Way. The galaxy isn't a uniform blob of stars. It has structure, a central bulge, spiral arms, and most importantly, a disk. Actually, two disks. The thin disk, where most stars are relatively young, less than 10 billion years old, and orbit in nearly the same plane, and the thick disk, composed of older stars with more chaotic orbits, tilted at various angles. "The thing people forget," Feng explained to his colleagues in a virtual meeting that would change the direction of the investigation, "is that where you come from in the galaxy tells a story. Stars born in the thin disk move differently than stars born in the thick disk or the halo. They have different velocities, different orbital characteristics. The same should be true for comets." Feng and his team analyzed 3I-ATLAS's velocity vector, not just its speed but its precise direction through three-dimensional space relative to the Sun. Then they compared that vector to the general motion of stars in different galactic populations. The results were stunning. 3IATLAS's velocity matched the kinematic profile of the thin disk almost perfectly. Its motion through space was consistent with an object that formed in the same region of the galaxy as our Sun, orbiting the galactic center at similar speeds, in the same flat plane where most stars and planetary systems reside. This wasn't some exotic visitor from the outer reaches of the galaxy, Feng announced at an American Astronomical Society press conference in April 2025. "This comet came from our neighborhood. Galactically speaking, we're talking about a visitor from a few houses down the street, not from across the world." The implications were profound. The thin disk of the Milky Way extends about 1,000 light-years above and below the galactic plane and spans tens of thousands of light-years radially. Within that volume are billions of stars, many with planetary systems. 3I-ATLAS could have come from any of them. Dr. Amaya Moro-Martin, an astrophysicist at the Space Telescope Science Institute, who had spent years studying debris disks around other stars, put the discovery in context. "What we're seeing is evidence that planetary systems throughout the thin disk are dynamically active. They form, they evolve, they eject material, and that ejected material, comets, asteroids, planetesimals, becomes interstellar. The space between stars isn't empty. It's filled with the debris of 1 billion different solar systems, all mixing together, a vast ocean of orphaned worlds." The realization transformed how astronomers thought about interstellar objects. They weren't rare curiosities from distant, exotic systems. They were common, coming from ordinary planetary systems scattered throughout our galactic neighborhood, and if comets from those systems could reach us, then our comets could reach them. Somewhere out there, Perhaps a comet from our own Oort cloud was passing through another solar system, observed by alien astronomers who wondered where it came from, just as we wondered about 3IATLAS. Understanding where 3IATLAS came from, the thin disk, was progress, but it didn't answer the more intriguing question: how did it escape its home system? What kind of violence is required to throw a comet into interstellar space at 40 kilometers per second? Dr. Jean Raymond, a planetary dynamics expert at the Laboratoire d'Astrophysique de Bordeaux in France, had been studying this exact problem for years. His research focused on how planetary systems evolve, how they become stable or unstable, and what happens to small bodies caught in the chaos. When a planetary system forms, Raymond explained in a detailed analysis published in the Astrophysical Journal, you start with a disk of gas and dust around a young star. Planets grow within that disk, sweeping up material. But the process is messy. Not everything gets incorporated into planets. You're left with billions of asteroids, comets, and smaller bodies on all kinds of orbits. For most of these leftover objects, their fate is sealed by the gravity of the giant planets in the system. Jupiter in our solar system acts like a gravitational bully. Any comet that ventures too close gets flung away, sometimes into the distant Oort cloud, sometimes into the inner solar system where it might collide with the sun or a planet, and sometimes out of the solar system entirely. Raymond and his team ran thousands of simulations of planetary systems with configurations similar to ours. Terrestrial planets close to the star, gas giants farther out, icy bodies beyond that. In each simulation, they tracked the fate of millions of small bodies over hundreds of millions of years. The results were striking. In a typical system, about 0.01% of comets get ejected into interstellar space. That might not sound like much, but with trillions of comets in a typical system, it means billions become interstellar wanderers. And the ejection mechanism is usually the same. A close gravitational encounter with a giant planet, typically something like Jupiter or Saturn, that acts like a cosmic slingshot. Imagine you're a comet on an orbit that takes you close to a giant planet, Raymond illustrated. You come screaming in, pulled by gravity. As you swing around the planet, you either lose energy and fall into a tighter orbit, or you gain energy and get thrown outward. If you gain enough energy, if the encounter is just right, you can exceed the escape velocity of the entire system, and once you do that, you're gone. You're on your way to becoming an interstellar object. But 3IATLAS's high velocity suggested something more dramatic might have occurred. Dr. Suzanne Falsner of the Max Planck Institute for Radio Astronomy proposed an alternative scenario: stellar encounters during the system's youth. Young stars don't form in isolation. They form in clusters, nurseries containing hundreds or thousands of stars packed into a relatively small volume. In such environments, close encounters between stars are common. If two young planetary systems pass near each other, their gravitational fields can overlap, creating chaos. Planets can be stolen, orbits disrupted, and small bodies flung away at tremendous speeds. 3IATLAS's velocity is high, Falsner noted, higher than what a simple Jupiter encounter typically produces. A stellar flyby during the system's first few million years could explain that. The parent star might have had a close encounter with another star, and 3IATLAS was caught in the crossfire, ejected at high speed as the two systems briefly merged and separated. The scenario was plausible but unverifiable. Without knowing which star was the parent, they couldn't check if it had indeed been part of a dense stellar nursery billions of years ago. The comet's origin story remained tantalizingly incomplete. While dynamicists puzzled over ejection mechanisms, spectroscopists were extracting secrets from the light reflected off 3IATLAS. Every molecule absorbs and reflects light at characteristic wavelengths, creating a unique signature. By spreading the comet's light into a spectrum, essentially creating a rainbow and measuring the brightness at each color, astronomers could determine what it was made of. Dr. Cyrielle Opitom, a spectroscopist at the University of Edinburgh, led an international observing campaign using multiple telescopes. The goal was to create the most detailed compositional analysis of an interstellar comet ever attempted. If 3IATLAS came from another planetary system, Its composition might reveal clues about that system's formation environment. The first spectra came from the Very Large Telescope in Chile, water, as expected. All comets are primarily ice, and water is the most abundant molecule in the universe after hydrogen and helium. But the interesting details lay in the trace constituents, the molecules present in smaller amounts. Carbon dioxide, abundant. Methane, detected. Ammonia, present. Cyanogen and diatomic carbon, confirmed. These were all common in solar system comets, suggesting that the chemistry of comet formation was similar in 3I-ATLAS's home system to our own. But there were differences. The ratio of carbon monoxide to water was higher than typical for solar system comets. The deuterium to hydrogen ratio, a measurement of heavy hydrogen isotopes that reveals information about temperature during formation, was slightly elevated, and there were traces of complex organic molecules, prebiotic chemistry that could, under the right conditions, lead to life. What the composition tells us, Oppitom explained in a comprehensive paper submitted to Astronomy and Astrophysics, is that 3I-ATLAS formed in a region of its home system that was similar to our Kuiper belt or Oort cloud, cold, distant from the star, rich in volatile ices. The slight differences we see might reflect a slightly colder formation environment or a different mix of primordial material in that system's protoplanetary disk. The detection of complex organics was particularly intriguing. Dr. Jennifer Bergner, an astrochemist at the University of California, Berkeley, analyzed the molecular data in detail. We're seeing molecules with 5, 6, even 7 carbon atoms linked together. These are the building blocks of biology, not life itself, but the chemistry that could lead to life. Every planetary system, apparently, produces this material. It's universal. The universality of comet chemistry had profound implications. It meant that the process of planetary system formation, from collapsing gas cloud to protoplanetary disk to planets and leftover debris, followed similar rules everywhere. The laws of physics and chemistry were truly universal, and if the chemistry was universal, perhaps biology was too. When I look at 3I-ATLAS's spectrum, Bergner reflected, I see home. Not Earth, but something like home. Another planetary system where water froze, where carbon chains formed, where the ingredients for life were mixed together by cosmic processes. That system might have planets. Those planets might have atmospheres, and somewhere on one of those planets, perhaps there's life looking up at their sky, wondering if they're alone, not knowing that one of their comets is visiting us right now. As the months passed and 3I-ATLAS faded from view, becoming too distant and dim for even the most powerful telescopes, astronomers turned their attention to a bigger question. How common are interstellar objects? Before Oumuamua in 2017, we had detected exactly 0. Theory suggested they should exist, but we'd never seen one. Then Oumuamua appeared, followed by Borisov, and now 3I-ATLAS. 3 detections in 8 years. Was this a fluke, or were we finally developing the observational capabilities to see what had always been there? Dr. Avi Loeb, a theoretical astrophysicist at Harvard, who had famously proposed that Oumuamua might be artificial, a hypothesis most astronomers rejected, led a study to estimate the population of interstellar objects passing through our solar system at any given time. The calculations were complex, involving detection biases, survey completeness, and assumptions about size distributions. But the results were stunning. At any moment, Loeb's team estimated there were approximately 10,000 interstellar objects within the orbit of Neptune. Most were small, perhaps the size of a car or house. Some were larger, like 3I-ATLAS. A few might be enormous, kilometers across, massive enough to have their own gravity shaping them into spheres. The solar system is swimming in interstellar visitors, Loeb announced at a press conference that generated headlines worldwide. They've always been here, we just couldn't see them. For everyone we detect, thousands pass by unnoticed. The space between stars isn't empty. It's an ocean filled with the wreckage and refugees from billions of planetary systems. Dr. Gregory Laughlin, an astronomer at Yale, extended the analysis. If the solar system contains thousands of interstellar objects at any time, and the Milky Way contains hundreds of billions of star systems, then the galaxy must contain an incomprehensible number of these wanderers, perhaps 10 to 26 objects, or 100 quadrillion trillion, more than the number of grains of sand on all of Earth's beaches. The Milky Way is a vast, interconnected system, Laughlin wrote in an essay for Scientific American. We tend to think of star systems as isolated islands, separated by gulfs of empty space. But that's not quite right. Every system is connected to every other system by a tenuous web of ejected material. Comets like 3IATLAS are the threads in that web, carrying information and material from one system to another. On timescales of billions of years, the entire galaxy mixes together. The implications for astrobiology were staggering. If organic molecules form universally in planetary systems, and those molecules are spread throughout the galaxy by interstellar objects, then the building blocks of life are everywhere. Some scientists began to seriously consider panspermia, the idea that life itself might spread between star systems, carried by objects like 3IATLAS. A microbe, frozen in the ice of a comet, could theoretically survive the millions of years of interstellar travel and be deposited on another world. We might all be aliens, Dr. Chandra Wickramasinghe, a proponent of panspermia, suggested in a controversial but scientifically grounded paper. Life on Earth might have originated elsewhere and arrived here on an interstellar comet billions of years ago, and life from Earth might already be spreading to other systems, carried by comets we ejected long ago. 3IATLAS isn't just a visitor. It's a messenger, a bridge between worlds, a reminder that in the cosmic scheme, we're all connected. On July 15, 2025, the International Astronomical Union held a special session in Tokyo, the first in-person gathering of the world's leading astronomers since the pandemic. The topic: interstellar objects and the new paradigm of galactic connectivity. Over 2,000 scientists attended, with millions more watching via livestream. Dr. Baylor Jones gave the keynote address, summarizing what had been learned from 3IATLAS. But he also acknowledged what hadn't been learned. We still don't know exactly where it came from. We may never know. The galaxy is too large, too dynamic, too chaotic to trace back with certainty. But perhaps that's not the point. Perhaps the lesson of 3IATLAS is that asking, "Where did this specific object come from?" is the wrong question. He paused, letting the packed auditorium absorb his words. The right question is, what does its existence tell us about the galaxy we live in? And the answer is profound. The Milky Way is alive with motion, with interaction, with exchange. Planetary systems don't evolve in isolation. They're part of a galactic ecosystem, constantly exchanging material, constantly influenced by passing stars and interstellar clouds. Every star system we see, including our own, is built from material that has been recycled, processed, mixed, and transported across vast distances. 3IATLAS came from somewhere, Baylor Jones continued. A planetary system not unlike ours, with planets and moons and asteroid belts. That system ejected this comet, maybe through a Jupiter encounter, maybe through a stellar flyby. The comet traveled for millions of years through the dark, cold void between stars, and then, by cosmic chance, its path intersected ours. We had maybe 2 years to study it before it disappeared forever. But in that brief window, it taught us something extraordinary. We are not isolated. We are part of something larger, something dynamic, something alive. The applause was thunderous, lasting for nearly 5 minutes. But when it subsided, Dr. Fung took the podium for the session's closing remarks. His tone was more contemplative. 3IATLAS fooled us. It looked ordinary. It acted ordinary. If we hadn't measured its velocity precisely, we might never have known it was interstellar. And that makes me wonder, how many other interstellar visitors have we missed? How many comets have we catalogued as part of our solar system that actually came from elsewhere but happened to be captured by the sun's gravity? How much of what we think is ours is actually borrowed from the stars? And here's the really unsettling thought, Fung said, his voice dropping. Right now, at this moment, there's a comet from our Oort cloud traveling through interstellar space. Maybe it was ejected by Jupiter 1 million years ago. Maybe it's halfway to Alpha Centauri. And maybe right now astronomers in another planetary system are detecting it, studying it, wondering where it came from. They're having the same conversations we're having, asking the same questions, reaching the same conclusions. We're all connected. We're all part of the same galactic story. 3IATLAS is gone now, heading back into the darkness from which it came. In a few million years, it might pass near another star, becoming that system's mystery to solve. Or it might wander forever, a frozen time capsule carrying the chemical signature of a world we'll never see. But it left us with a gift more valuable than any physical sample could be: perspective. We live in a galaxy that is not a collection of isolated systems, but a unified whole, connected by invisible threads of gravity, motion, and exchanged material. Every star we see in the night sky has likely both received and sent interstellar visitors. The Milky Way is engaged in a billion-year conversation with itself, and objects like 3IATLAS are the words being spoken. Somewhere out there is the star that lost this comet long ago, a sun much like ours, possibly with planets, possibly with life. They don't know that their comet visited us. They'll never know that for a brief moment we and they were connected across the vast distances of space by this frozen messenger. But we know. And knowing changes everything. The galaxy is smaller than we thought, more intimate, more connected. We're not alone on our island, isolated by the void. We're part of a neighborhood, cosmic neighbors sharing material and stories across the light years. 3IATLAS proved that. And in doing so, it reminded us of something we should never forget. We are children of the Milky Way, born from its dust, shaped by its forces, forever connected to its dance. Our story is not separate from the galaxy's story. We are the galaxy, awakened, looking back at itself and finally beginning to understand.